Okay, let's get started. So today's topic is semantic parsing. So we're switching from the syntactic parsing that we saw on Monday to semantic parsing, which involves converting natural language into some sort of meaning representation that can then be potentially executed, say by a robot or by some other agent as a form of instructions. Before we do that, I forgot I had to go over the grading change, so let me do that. So since we have 3 homeworks this time, the homeworks are now, let me make this bigger, 30% of your grade, and it was formerly 20%, so the quiz percentage decreased as well as the final report percentage. So this is what we'll be sticking with. If you want to try and estimate your grades or plan them, then use this. Yeah. Yeah, so you'll have one more quiz. I think you've had 4 so far, so you'll have one more, which will make this easy. And that will be due end of next week. All right. So with that out of the way, whoops, that's not what I wanted to do. All right. Was there anything else I wanted to say? Probably, I don't remember. Let's just get started with the content of the lecture. So in semantic parsing, our goal is to actually go from natural language input to some sort of response. So this could be like telling a robot to navigate itself to the kitchen. So we want to tell the robot, go to the kitchen, and our ideal outcome is the robot listens to us and then goes to the kitchen properly. However, this is a little bit complicated because the robot probably can only understand some primitive commands like go left and go right and go straight for X number of feet and so on. So we might have to have an intermediate process that converts the natural language utterance into some sort of meaning representation or sequence of actions or something like that, that our executor, in this example, a robot, can then understand and easily execute to arrive at the ideal outcome. So in contrast to syntactic parsing, remember there our goal was to just obtain some sort of linguistically meaningful representation of a sentence. Here our goal is more task-oriented. So this meaning representation could change depending on what task we're looking at. The executor and response could vary, and we'll see a bunch of different types of semantic parsing situations in this lecture. So one of them is question answering. This is a very popular setup when you want to do QA over, say, a database or a collection of tables from the internet or some structured source of knowledge. So if I wanted to query, say, a database formed by, I don't know, the census or something for how many people live in Seattle, I might need to convert this query into a SQL statement, which can then be executed by the database on the database and give me the correct entry in that database that matches my query. So you can see already that this problem starts looking a lot like translation. I have how many people live in Seattle, and I may want to create select population from city data. So this is like some table that I have where the city equals Seattle. And much of this task revolves around this first part. So given the natural language utterance and given the natural language utterance, can you produce this intermediate logical form? We rarely are concerned with the executor that's usually just given to you. It could be some existing database or some robot or whatever. We just assume it can execute any valid action in this, like whatever language this intermediate representation is in. And our task is mainly to do this translation from natural language into whatever that meaning representation is. All right. So like the example I was referring to at the beginning of class, this is also a very useful framework for instruction following. So if you want to tell a robot, go to the third junction and take a left, it's maybe a little bit complicated, right? If you look at this language, it says there's like some loop type statements, move to forward location until the current location has a junction, and so on. So you can see that this is not SQL, this is some other type of language. And throughout this lecture, we'll keep seeing different forms of this intermediate logical form language. Whatever it is, it really doesn't matter as far as the algorithms that we'll discuss. But it can vary depending on what task you're trying to solve. So the critical challenge in semantic parsing is that we very rarely observe the latent meaning representation. So this is in contrast to what we talked about with syntactic parsing, where we assumed we had access to some sort of tree bank where linguists had labeled each of these sentences with these trees, and then we could just train a parser to output those trees. Here, it's rarely that simple. So, you know, there are data sets where you have a question paired with SQL query, but there are a few data sets that are at scale where you have like an instruction paired with some sort of language, as these things are kind of specific to a particular executor. So the interesting learning challenge here becomes, what if you just have the natural language question and the expected output after executing the instruction, but you don't actually know what that intermediate logical form, what the correct logical form is? Can you still have some model that learns, you know, some sort of latent structure that can correctly execute to the intended answer? So this is also, you know, as an example, let's take this setup where if I wanted to make this task easy for a model, I might collect, you know, tens or hundreds of thousands of question SQL pairs, and then just train, like, fine-tune a T5 or whatever on this task, like a normal sequence-to-sequence model. But if I only have how many people live in Seattle and the answer to this question, 620,000, now the process of coming up with a SQL query becomes a little bit difficult. So if you want to use the database, which you should in all cases, right? You actually need to come up with some SQL query that you can execute over the database, but your only signal could be, is the answer you get from running your SQL query equivalent to the one that that's in your data set? So the learning signal is not as strong. This is a case of weak supervision where you don't know the ground truth meaning representation, you only know what the correct answer after executing that meaning representation is. And we'll talk about a variety of ways to learn models in this kind of setting. Okay, so there are many connections between semantic parsing and syntactic parsing. The earlier work in this area tended to look more like the stuff we talked about yesterday, like you would define a grammar over certain actions, you would have rules in your grammar, you know, like the word to has to have some different arguments, like where are you moving to and what are you moving and so on. And you can, you know, define these kinds of non-terminals for every word in your language, and then have these composition rules that you can eventually compose into something that spans the entire sentence. So This is what is now called the classic approach. But unlike constituency parsing, which we saw in the last class, where still like these CKY type algorithms are dominating, the neuralization of this process is mostly in how do you encode those rules? You can maybe encode them with vectors instead of just discrete rules, and maybe you can share information there and do better. Here, in semantic parsing, it's much more common to just get rid of the grammar completely and frame this as a sequence-to-sequence problem. So getting rid of this grammar engineering part, which was very difficult to engineer in these kinds of situations. If you imagine in the syntactic parsing case, linguists generally have an agreement over which rules to include in the grammar for a particular language and so on. But here, like, you might have some specific robot that you want to interact with, and you really need some specialized knowledge and time and expertise to come up with a valid grammar mapping natural language to the internal formal language of the robot. So one of the very first papers just essentially took a neural machine translation sequence-to-sequence setup and just applied it to semantic parsing. This is assuming that you know the ground truth logical form. So this is like the SQL query or the robot instructions or whatever. So you see here what Microsoft jobs do not require a BSCS. This input gets processed by some encoder network and then goes into a decoder network with attention, and the decoder is generating the ground truth logical form. So this work assumed that you had pairs of the input natural language and the output logical form. Of course, if you have these pairs, it's very easy to do this, but there are still some tricks that you might want to employ in the sequence-to-sequence setup to make the task easier for the model. So what are some issues that you could foresee with doing semantic parsing as a sequence-to-sequence problem? Yeah, exactly. So here, if you look at this or a SQL query or whatever, there are very strict constraints on what is and what is not a valid logical form, right? And so if we're generating from some decoder model and we're producing a token at every time step, there's nothing that guarantees that this is going to become a valid semantic parse, right? And so in natural language, this is the same, right? There are some constraints, but they're definitely not as strict as in this case. If a parentheses is not matching, your executor won't even be able to run the query. So yeah, there are strict constraints that you might want to address during the decoding process to make your semantic parser better. Okay, so let's take a look at a concrete example. This is from the dataset Wikitable questions. So here you have a table, and you have a question about the table, and in the setting in their dataset, you do not observe the logical form. So you can see that this is not exactly a SQL query, but it's something kind of related. Like here, you want to select an athlete, where the nation is South Korea and the year is after 2010. So they're all, there are many different types of formal languages that are used here, but the methods don't really change. So if we were using just normal sequence to sequence to go from this question to this logical form, we would take as input the question in our encoder. That's all standard. But the decoder is where things start to get a little tricky. Here, we might have a vocabulary of thousands or tens of thousands of tokens, right? Because we have to include all of these words that could potentially be cells in the table. And many of them might not be valid at whatever position, but depending on what you've generated in the past. So the green marked boxes here are the ground truth that you're trying to generate at every time step if you had full supervision. And the red marks things that are just not valid at all. So you should never be able to generate them. And remember, this is only a subset of the vocabulary. But in this particular meaning representation, every logical form begins with an open parentheses. So none of these other things are valid. And here you can see that if you close it, so your logical form is empty, then this is not valid. Similarly, if you choose this athlete column, you need to close the parentheses, so nothing else is valid except this. So they're very strict constraints. And if you're doing something like sampling from the distribution at every time step, you will have a chance of generating any of these other tokens, which would immediately make your logical form invalid. So this motivates what's known as constrained decoding, where if you know the constraints of your meaning representation ahead of time, you can actually encode them into the decoding process. So you can say, for instance, you get the model's predicted distribution at this time step, let's say this time step here, and you make all the probabilities of words that you can't produce some very low number before you actually go through the generation step. So this could involve, writing some rules, or maybe keeping track of these open and closed parentheses, keeping track of which operators have been generated, so if they have constraints on what can follow them, and all sorts of things like this. This is kind of a hack, though, right? Because you're training this model just as a normal sequence-to-sequence model. This is only a test time that you're kind of just masking out your vocabulary, masking out the things that you should not be able to produce at any time step, and then doing the generation. So that's what we just talked about, this constrained decoding. The goal is to avoid any invalid parses or logical forms generated during the decoding phase. And this requires you to have the ability to write some sorts of rules to constrain the decoding process and get rid of these invalid parses. Okay, so yeah, this one is what we talked about, this token-based decoding. The output space is token by token, but you're applying these constraints at each time step. You could also constrain your output based on a grammar. So instead of the model producing tokens, it might produce rules that are later expanded out with templates, and you can kind of do the constraints that way. So we can take a look at some of these approaches. This one, I think, is particularly interesting, sequence to tree. So you know that in these kinds of logical forms, you have a lot of variables that are always going to be encoded. The variables could come from the columns or cells or entries in the database or operators or whatever. So here, and this is another application of semantic parsing, is like restaurant or travel booking systems. These were kind of the initial motivations for this research. So if someone calls up, like Delta Airlines and says, give me all the flights from Dallas leaving after 4 in the afternoon, you might convert this into some sort of structured representation of this query and then execute it over your travel database to get the relevant flights. So you could just generate this logical form token by token, but you could also generate it kind of hierarchically. So you generate the first level here, and then you see that there's this kind of blank or filler token, this N here. So the way this works is that every time you produce one of these n tokens, this is now used to initialize another pass of the decoder where you generate what goes into that filler token. So you can see here that we produce the word and, so that's associated with this, and then we produce 2 more of these filler tokens. These are going to be associated with both of these conditions here, this greater than departure time greater than 1600, and from like the origin being Dallas. So you can see this first filler token is used to produce this condition greater than 1600. The second one is used to produce from Dallas. And this one, there's another level of decoding. I don't really understand this logical form, so yeah, but you can see that the idea is to make sure that this is kind of following the specifications of the formal language by making the decoding process easier. Like you generate this high level structure, then the second layer structure, then finally you generate all of the tokens that are involved to fill in these arguments. So this kind of approach is shown to have fewer errors than what you might get in a linear left to right decoding fashion. All right. So at this point, like all of this stuff that we've talked about assumes that you have full supervision. So you have the question and you have the associated logical form and you have a large training data set of this. Before we go into the training methods, I wanted to quickly show an example from GPT-3 of how this could work now in 2022 and why we might not even need to do this kind of training at a large scale, at least for simple things like restaurant reservation or something like that. So let me go to this. Refresh. Okay, so I made this prompt, which, so all of these come from the Wiki SQL dataset. There's actually an associated table with all of these questions, but I just ignored that because it's annoying to put a table into here. Although I'm sure it would work, but it would look weird. So here you see I have 3 questions. Okay, sorry, maybe I'll give it 4 questions. I have 4 questions paired with the associated SQL query. So who was drafted with the 3rd pick of the 1st round? This assumes you have some table called my table that has all of this information about this draft, and then you want to output something like select player from table where round equals 1 and pick equals 3. And you can see I selected these such that they're all like kind of from the same domain. They're all about this kind of sports draft. But we could see if this kind of thing can generalize, given just these 4 question SQL pairs, to arbitrary questions that you might ask about a table or a database. So first, we can try a test question, a held out question that is in domain. So here I'm asking it, what was the result of the game played on April 16th with Philadelphia as a home team? Now, of course, we don't know what this database looks like, and we don't know what the columns and all are, but at least we can see if the logic of what it produces is reasonable. So let's see. Okay, so it said select result. That's pretty good from my table where home team equals Philadelphia and date equals, so that is like basically what we wanted. And it did this with only 4 question SQL pairs in the prompt with no training whatsoever. So that's quite impressive. And maybe we can just put this into, now we have 5 prompts. And I wanted to try another example. Yeah, so this one, obviously has nothing to do with this sports draft. It says, who's the incumbent for the Oregon 5 district that was elected in 1996? But you could imagine the logic is pretty similar. If it learns to reason, if it learns the reasoning behind how to do this translation, maybe it would, like the patterns are quite similar, right? You just need to select something and give it the appropriate filtering condition. So let's see what it does here. So select incumbent from this table where district equals Oregon 5 and year equals 1996. I guess that was a pretty straightforward question, but it's still interesting to see it work on this different domain. So yeah, does anyone want to give a question that you might reasonably ask about some sort of structured knowledge source? We can try it with maybe you can just incorporate this into our prompt. So now we have 6 questions. Okay, yeah, that's a good question. Let's see if it, oh, this is interesting. So it had many conditions. I guess we could make this more complicated, right? Like, we've done only selects. Oh, I guess there's this count-based one. Maybe you can try out the count. So like, how many times did it rain in Amherst in June 2018? I mean, that's interesting. I guess that makes sense. And weather like rain. It's not bad. I guess we could also try to see if it generalizes to something outside its training prompt set. So we could say, what was the maximum? I'm going to ask like how much was the maximum amount of rain that it got in this month, but I'm not sure what the best way to word that is. Any ideas? Of rain, like daily. I feel like this is not a great question, but let's see what it does. Oh, wow. So, like, we didn't tell it about this max operator at all. Like, it was, oh, wait, I guess it got this min operator. So, yeah. So, do you have a question? Fail. Let's see. All right. In Amherst, MAN. Okay, I mean, this should be 0, I guess. Select count distinct. Yeah, I guess if I change this, then, or maybe I could say flu. Oh, that's pretty interesting. Yeah, but like the count distinct, I mean, GPT-3 has seen several SQL queries in its training data, in its pre-training data. So, but yeah, still very impressive. I mean, this if you had it in 2018 or 2016, would have been far superior to the best, SQL translator that currently exists, that existed then. Like, any of those models that we just discussed would struggle with these kinds of things. So yeah, it's you know, quite impressive. Yeah.
Are there any methods for a system like this to kind of detect when the question maybe has some ambiguity, and then perhaps like open the dialogue and say, hey, what do you mean?
Yeah.
Which cases are fluid? Like what?
So the question is, you know, sometimes the natural language statement might be ambiguous, like there might be multiple columns that it could refer to, or multiple interpretations that could both be parsed in different ways. So yeah, there has been quite a bit of work, especially recently, on when the question itself it lacks information, instead of the model just producing one of those interpretations, or worse, some sort of mixture of them. Perhaps it could learn to ask for a clarification, and once it receives that, then it is able to you know, produce the right query. So yeah, I'm not remembering off the top of my head the particular papers, but there is a lot of work in this area. I mean, it is something that we eventually want our models to do, right? If you produce a question, they should be able to ask for further inputs, or maybe the question asker's premise was just wrong in general or didn't make sense. Yeah, so that's a great point. All right, so this even is, of course we did no training here, but it assumed that we had some pairs like this. And you can imagine that this is actually quite manageable to achieve with many different situations. Like if your task is not that complicated, maybe this is just a good route to go, right? Just put it into GPT-3 or some huge language model, put as many examples as you can make up yourself into the prompt, and you probably have a very strong baseline, at least, for some more custom built system. But yeah, so that's the case that we mentioned here. So you can either train a model from scratch to go from X to Y, or you can use what we just did, like in context prompt learning to, or like zero shot, I don't know, few shot in context prompt learning to get some outputs. But that always assumes that you have access to the Ys, right? Here the X is the natural language, the Y is the meaning representation. So this task here is quite trivial. The interesting task is if you have the natural language and you have the result of executing the correct meaning representation, but you don't have the Y, the meaning representation itself. So you have in wiki table questions a question, a relevant table about which the question is asked, and then the answer to the question, which might be a cell in the table. And then you're asking it, you know, given this question, the task is essentially to find the meaning representation that results in this Z as the output. Yeah. Yeah. So in this particular table, yeah. So it depends on it. You know, one criticism about this kind of data set is that no one would really ask these questions about a table that's so small. But, you know, this was developed as a way to just test out different semantic parsing algorithms on a simple-ish data set. Many of the questions are highly unnatural, like they might contain a lot of nested conditions or other things. There are also data sets that are similar where it's like question to SQL statement, where the SQL statement is insanely complicated. It has like multiple joins and all of this as a kind of challenge task for these models. And we are making progress on all of these. But yeah, I agree with you. In a practical setting, this question is, you know, kind of meaningless, but yeah, it's more for demonstration. Okay, so we're going to focus on this right-hand side for a while now, the weakly supervised setting where you don't observe the logical forms. So there are a couple of different methods that we can use to train these kinds of models. So we'll start with probably the simplest one to understand and implement, but then talk about why it's kind of limited and why we might need to use some heuristics or other kind of hacky techniques to make it feasible to actually do this. So in maximum marginal likelihood training, we have this setup that was described earlier. So we're given the question, this X, the table, this W, and the answer to the question, this Z, and we're not given the Y. Our goal is to maximize the probability of the correct answer given the question. I mean, that's what we want to do. But we can't just obtain an answer from a question, right? We need to run the question through the executor over the table to get the correct answer. And so that entails having some sort of logical form that can be passed into the executor. So our real learning objective then is to maximize the probability of this yi that leads to the correct answer z. So if you look at this summation here, we are summing over all logical forms y that, when executed over the table w, lead to the correct answer z. So in this equation, this big Y here is a set of all valid logical forms that execute to the correct answer Z. This is very difficult to obtain, right? There are many, many different logical forms that could all end up evaluating to the correct answer that's given in your data set, this Z. And also, it might be hard to enumerate all of these possible logical forms. So this is actually kind of a search problem in practice, where you don't have an easy way to enumerate all of the logical forms that evaluate to Z. And then, of course, if you had this, you could simply just apply this objective where you sum over all of them and try and maximize the probability of this set of logical forms, because all of them execute to the correct answer. You can also see one of the limitations of this weak supervision approach. It treats every single logical form that executes to Z as a valid parse, and we're trying to maximize the probability of all of those logical forms. But of course, that's not true, right? Like if you look at this, the answer is Kim Yuna, but I could have also asked which athlete won 2 medals and was from South Korea, and I would have gotten the same exact cell back, but that isn't the meaning of this question, right? It just happens to execute to the same answer. So that's an inherent limitation with these weak supervised approaches, is that you have a huge set of logical forms potentially that executes the correct answer. You don't really know which ones are matching the intent of the question and which ones just randomly happen to align with the correct answer. And if your set Y, the big Y here, contains a lot of what's called a spurious logical forms, so these are logical forms that execute to the correct answer, but you don't want to increase their probability because they don't match the semantics of the question. If the set is dominated by such logical forms, then learning becomes very challenging. Your signal is not putting a lot of probability on the correct logical form. It's distributing that probability mass over a bunch of other incorrect logical forms. So these are some of the many challenges associated with this kind of process. And to address some of these challenges, there are essentially the most popular are these kind of structured learning approaches. So here you acknowledge that you probably are not going to be able to enumerate the entire space of logical forms that evaluate to Z. And also you acknowledge that you have this issue with some of those logical forms not being correct. And so you might want to have a method that searches the space of logical forms and maybe finds a subset that evaluate to Z. And sometimes maybe you execute the search and you don't find any logical forms at all that execute to Z. In that case, you can even use kind of approximate training examples here. The important part with some of these structured learning methods is that they aren't going to just use this simple, like, maximize the probability of these logical forms. You can use other loss functions here that make it possible to integrate your, heuristics, search, or whatever. One common thing is to use margin-based loss functions. So here, you might find one logical form that executes to the right answer and one that executes to an incorrect answer, or several that execute to incorrect answers, and then you can basically train your model to prefer the one that executes over to the correct answer over the incorrect ones. So note that you can do that without this kind of probabilistic loss function. Okay, so in all of these settings, the important part is how do you approximate this big Y, the set of logical forms that execute to Z. So there are two general types of methods that are used for this process. There's online search and offline search. So in online search, you are updating the set of logical forms during training. So as your model changes and is backpropped into and its parameters change, you might be able to do you might be able to redo your search and get a better estimate of the logical forms that execute to Z. So this is good. You get better candidates potentially, but it's also not efficient because you have to run a search before you actually are able to train on a particular example. In offline search, you do some sort of search process before training your model. So this means maybe you have some very hacky search method that does like some sort of string matching maybe on the logical forms, or some other method. You have a static set of candidates, and you can then easily apply some sort of maximum marginal likelihood training or other method to get your model. So this is much more efficient because you don't have to do the search during training, but your candidates are going to be worse on average. So I think most successful methods try and incorporate online search, and there are some ways to try and make it more efficient. Maybe you terminate the search early, or maybe the search itself is part of your model training process.
What's the second form, like for offline search? Do we do some form of a retrieval kind of function that we have some candidates and we need to retrieve one from them? And even at time of inference, we use the same like heuristic to find some candidates and then retrieve one of them.
Yeah, so the question is, for offline search, how do we get the set of candidates, right? Are we doing kind of a retrieval-based approach where we already have some huge set of logical forms, and then we search over those logical forms to find the correct or whatever logical forms that execute to the answer? Usually it's not like that because there's just so many logical forms, right? You can't just enumerate over all of them.
I think my question was that suppose we have those candidates, do we like learn a generation model, or do we learn a model which is similar to retrieval kind of?
Oh, so you mean after you come up with these candidates, so is your question like, do you learn to generate those logical forms, or?
Do we just try to like find the best?
No. So all of these approaches will try and generate the logical form in some way. So they, I mean, if you're retrieving from some existing set of candidates, then you're always going to be inherently limited, right? If you get a query whose logical form is outside that set, you will never be able to answer it. So all of these algorithms will have a way of incrementally constructing the logical form that's customized to a particular query. Okay, so finally, I'm not going to talk too much about this because it it's kind of hard to get this to work, but you can also apply reinforcement learning for this problem. So it's kind of similar to what we were talking about with the structured learning, except here in reinforcement learning, you would basically sample a logical form and then check whether or not it executes to the correct answer, and you have a reward, which is like a binary reward in the simplest case, right? So it's 0 if it doesn't execute to the correct answer and 1 if it does. If you're familiar with reinforcement learning, you could probably tell that this is a really bad reward signal because most of the paths that you sample, at least initially during training, will be 0. And so then you might have to resort to some sort of approximate rewards rather than this 0 and 1. So maybe a logical form that you sample will get some partial credit if it has some overlap somehow with the question or with the answer, but you can only go so far with these kinds of methods. So it's very related to structured learning, but yeah, you're trying to directly maximize this reward, so the reward design is a huge factor, and it's kind of hard to get that to work. Okay, so let's take a step back and talk about if we want to build a sequence-to-sequence model to solve semantic parsing, what do we need? So our goal is to convert these programs, the logical forms, to some sort of sequence of actions. So one action could, for example, be generate the select operator or generate the arguments for this condition or something like that. So in the simplest case, you will just say an action is generating a token of your logical form, but you could also imagine some grammar-based decoding where you're not just producing a token at a time. Once you have a way of decomposing a logical form into a sequence of actions or steps, then you have to figure out which of these actions are valid at every time step. So if I've generated select, I probably don't want to generate select again, right? That would be invalid. Then once you have produced an entire sequence of actions, if your actions were not actually one-to-one mappings with the logical form, maybe you had some grammar or something, you need to be able to convert them back into the logical form, and then you need a way to execute whatever you produced on the context that is given, like a database or a table. And finally, what we've just been discussing, if you don't have labeled logical forms, you need to choose one of these alternate methods of training in order to, improve your method that's actually converting the natural language into these action sequences. All right, so let's take a look at one of my own works previous works that explores this kind of structured learning method in the context of semantic parsing. In this case, it's very similar to wiki table questions, except you don't just get one question, you get a sequence of questions that are all related to each other. So like, how much protein is in an egg? The model should answer this, and then you might have a follow-up question like, how many carbs? And this question refers to the egg, but the egg is kind of implicit in the second question. So there's both the semantic parsing challenge as well as the resolving references to previous questions and answers, which adds a further challenge. So all of the questions here are about a table. So here we have this table about the Women's Water Polo World Cup, and we have some countries, medal counts, and rankings. So I might get a question like, which nations competed in the FINA Women's Water Polo World Cup? And here, of course, if I was using SQL, the correct answer might just be like select nation. So I would want my model to be able to produce this. And then I might get a follow-up question. Of these nations, which ones took home at least one gold medal? And so here there's a new operator to SQL called subsequent, which we made up, that kind of refers to the output of the answer to the previous question. So here you take all of these nations and you apply this condition to them, where gold is not equal to 0, or I guess this should be where gold is greater than or equal to 1, and you would get these 4 countries. And then you can further do some filtering on those. So you can have, this big chain of questions, some of which might refer to previous questions, some of which might be completely different. Okay, and so in this case, this is a weakly supervised problem, so we do not know the ground truth SQL statement. We only have data that looks like this. Which nations won exactly 1 gold medal? Answer, Hungary. So this is the Z, this is the X, we have the table, the W. We are just looking for the Y that executes to this answer. So in this question, and given the table from the previous slide, the logical form that we want to produce looks like select nation where gold equals 1. That's our goal. So let's look at how we decompose this into a sequence of actions that are needing to be predicted. So the first thing we do is we start with a start state. So here our current state is start, and we have access only to the question and the table. And so now we have some function, which we call pi here, that takes a representation of the current state, which is currently just in start, and also takes a possible action that you could produce given this state. So this is where you can encode which actions are valid or not valid. Like here, given just no previous context of logical form, you probably can only produce a SQL operator like select or count or whatever. And this pi function will take the representation of the state as well as the action and then output a score. And we are going to learn this function. So hopefully through the learning process, it will give actions that we should take in order to get to the right answer a higher score than actions that we shouldn't take. So here we see 2 possible actions that we could take: select nation, which is what we want the model to do, and select rank, which has nothing to do with this question, but is still a plausible action that the model could take, so we need to include all of these things during the learning process. So given that we have these 2 potential actions, you can sort of consider this as a beam search, where our scores are coming not from a language model, but from this pi function. So we might take the top 2 highest scoring actions and then kind of expand both of those and do some pruning and so on. So here, let's say we're expanding down this rightmost column. So we select rank, and now we arrive at this new state, state 2, where we have the question, we have the table, and we also have this partial logical form which we've already generated, select rank. So now, given all of that, our pi function is going to score all these actions, and then it decides to, the highest scoring one is conditioned on the gold column, then equals 1, and then we get 4. So this is the rank of Hungary, but not the actual name of the country. So this whole path is bad because this very first decision that was made was incorrect. All right, so let's take a look at the correct path. Here in state 2, we have produced select nation, so we're on a good path. But we could also, go wrong in the second action here. So here, the correct action is conditioning on the gold column, but we could also condition on the rank column here. And we see that problems begin to arise when we have multiple paths that evaluate to the correct answer, Hungary, but we don't have any way of distinguishing between this path and this path. So although the blue path is the one that we want to maximize, we might, in our beam search, actually end up with a path like this one, where it executes to the correct answer, but it's not really the right path, so it doesn't give a great learning signal for the model. That said, this is not entirely unreasonable path during training, because at least part of the logical form was correct. So in general, these kinds of approximate search methods, even if they yield logical forms that are incorrect, you can still learn a lot from those. And then if you're applying online search, as we talked about, your paths will start looking better and better as you continue training. Okay, so then our objective function, once we've completed this beam search, we probably found some good paths and probably found some bad paths. We want to maximize the score of the best path that we found and minimize the score of an incorrect path. And there are a couple ways that you could do this. What we chose to do is find the incorrect path that is like the worst and minimize its score, and maximize the score of the best possible path. Because early on during training, a path might get a pretty bad score even though it's correct, so you don't want to be like down-weighting such paths. And really most of the struggles in training these kinds of models is at the initial training phase, when the model is really uncertain between many plausible choices. The error signal quality matters a lot. So one interesting question is what you do if you run this search using your current pi function and you don't find any paths that evaluate to this answer at all. In this case, you don't have any way of minimizing this objective function. So, and this happens a lot early on during training, where these pi scores are kind of meaningless, so your search is likely to fail. In these kinds of settings, you can develop kind of approximate rewards. So one thing that we had to do to make this work is use paths that had some sort of overlap with the correct answer, even if it wasn't exactly the answer. So for example, if we just terminated after select nation, we would return all 5 nations in this table, one of which is Hungary, but the remaining ones are not part of the answer. Still, we can say that this path is better than any path originating from select rank. So you have to apply these kinds of approximations to get some data to train on. Yeah, so high level, and this is, I'm showing this basically because it's kind of an example of how most of these methods work, is that in this kind of setting, what you do is you first do a search to obtain some approximate reference parses. Even if they're very wrong, there might still be something good about them. And then you just train your model to favor the best parse that you found in your search and downweight some of the worst ones that you found in your search. And you just let that keep going. Your model will start to assign more reasonable scores to things that you find in your search. Your search will start producing better and better logical forms until eventually you might have a good semantic parser. So, we proposed this nice little learning algorithm for this data set, and it was pretty bad. Like, the percentage of time it was able to correctly answer all of the questions in the sequence was like 3%. And the probability of it answering any one question correctly was like 10%. So, we I mean, we made some progress. Like, it's way better than random, but it's still pretty bad. And there were a couple of people who built on this approach with more powerful neural networks and so on. And then after a couple of years, this group at Google, they just decided to get just ignore this entire fancy learning algorithm and just put the question and the table into a transformer and generate the text of the answer. So this has no logical form component at all, and yet once you scale this up to big enough transformer, and especially if you pre-train that transformer, it started getting really strong numbers, like 25 or 30% on a single question. And I think now the performance of the best model on this task is not doing anything interesting at all in terms of learning, but just big scale transformers seem to be pretty good for doing reasoning over tables, even without an explicit meaning representation. So it's kind of another one of these results where simply scaling up one of the models that we've discussed in this course outperforms everything that had come before it. Yeah, I mean, you can see that in these kinds of approaches, you are training from scratch. So that is a big limitation, and sometimes it holds you back. Even if you have a nice algorithm, it's just, yeah, you can't get over that hump if you have a small data set. So pre-training and then fine-tuning and things like that are much more valuable than any clever trick you could apply and then train from scratch on your small data. Okay, so I think that's all I wanted to say. Are there any questions? Yeah. Yeah, so remember that, so the question is, how are we determining which is the correct or best path from the search? Remember that we have in our data set the ground truth answer, like this Z, and so we can use this Z to filter or rank the possible paths that we get. So for example, here we've shown 3 paths in this simple figure. 2 of them execute to Hungary, which is the ground truth answer. So immediately it's obvious that these should be preferred over a path that executes to something that's not Hungary. However, if you have a bunch of paths where none of them execute to the correct answer, then you have to use some approximations, like, okay, well, maybe this one executes to a bunch of cells, one of which is Hungary. That should still be preferred over this one, which executes towards just 4. Yeah, does that make sense? Yeah, so that's another thing you can do. The point was, how about this path that we get? It will probably contain words that match with the query if it's a good path, right? So here we have nation, we have gold, we have 1 and 1. Can we use that to score the paths too? Yeah, you can certainly do that. I think we might have even done that also. You can see how it becomes a little hacky after a while, but yeah. Any other questions?
So with an approach like this, where you have the executor, and you probably have to train the system now over again for a different executor. Okay. And do just kind of scale it up, do large language model approach. Does that tend to generalize between executors?
I mean, so it depends. Like we just saw with GPT-3, that probably will generalize because it already did that with no training at all. But something that you train or fine tune yourself on one particular executor, which takes in its own logical form or language, that will not generalize to any other thing. So you'll have to maybe fine tune that again or do something else. All right, so see you on Monday.